we've added maximum likelihood to our toolbox, and it's a very powerful tool, but it also has flaws and problems. And these flaws and problems often occur when you have a limited amount of data. So now, for the sake of the argument, assume that we can only do 2 coin flips. And you might say, well, a coin flip is not expensive. Why don't we just do 10 coin flips? It takes a couple of seconds. Well, that's true, but a lot of experiments take significantly more time and more money. So you might only be able to do 2 experiments, and you still want to infer information from that. So for the sake of the argument, let's assume we only have 2 coin flips at hand. And now, these 2 coin flips both show up heads. And now we remember that the maximum likelihood estimate was the number of tails over the number of tails plus the number of heads, which is the total number of flips. And that's 0 over 2 in our case, which is 0. And that's quite extreme, right? And that's a problem. Why? Well, even if you have a fair coin, which means that it turns up heads in 50% of the cases and tails in the other 50% of the cases, you have a 25% chance of showing this result. So it's kind of not that unlikely that the coin might be fair. But the maximum likelihood estimate is only a so-called point estimate, so you have to pick one particular value. And this leads to a phenomenon which is called overfitting. Okay? Because it's a point estimate, it is overfitting to the data, and it is not taking into account that it's not that unlikely that the coin might still be fair or might just be slightly rigged, slightly biased towards heads. Okay? But how do we counteract? How do we cope with that problem? Well, typically we have prior beliefs. For example, if somebody wants you to place a bet on the coin, you might assume that this person has biased the coin so that he or she can make money. But you would probably assume that this person is not stupid and would only bias it slightly so that it shows up 55% of the cases heads and 45% of the cases tails. And it would be fairly stupid to bias it so much that it always shows up heads, because that's fairly easy to prove. But how do we incorporate this mathematically? And the answer is surprisingly simple. We just assume that the parameter is itself a random variable, and that actually justifies this notation that we have, which is the probability of a flip showing a result given theta. So this was already kind of a notation that implied that theta is a random variable. Okay? And now we can have distributions over thetas, and we can incorporate this notion of, okay, a fair coin is still probable or still possible. And this might help preventing the overfitting. And we will have a closer look at this technique now. Now that the parameter theta itself is a random variable, we have to think about the implications of this. And we would still like to incorporate our data, our observations, of course. And to do that, we gather our data, our observations, in a set, and this set is denoted by a calligraphic D. Okay, so that's our data, our coin flips that we've observed so far. And what we're interested in now is the distribution of our parameter theta after seeing the data. And we do that by conditioning on the data. This is also called the posterior distribution. We'll talk about this in a second. And now that theta is a random variable, this means it can take on specific values x. Okay, so we have a random variable theta, and the random variable takes on scalar values x. And because it's a probability, the parameter theta is a probability, so that means x has to be between 0 and 1. Okay? Now, to understand what is happening here, let's take a step back and look at what maximum likelihood was. Okay? So maximum likelihood, the maximum likelihood estimate theta MLE, was actually maximizing the following term. Let me write it down. So that is the likelihood. The likelihood is the probability of the data given the parameter. And we were maximizing this with respect to theta. And now what we're interested in is the probability. Sorry, I need some more space here. Is maximizing with respect to theta the probability of theta after we have observed our data. Okay, so we've exchanged the positions of the data and theta. And it's not obvious what this exactly means. But we can see that it's different, and in general, it's not the same. Okay? And the next slides will be talking about what the differences are and how this can help solving this problem of overfitting when you have too little data at hand. First, let's start by analyzing this new term. This term where we condition our parameter theta on the data. Okay, and now Bayes' rule tells us that this is the same as this fraction here. And this fraction consists of three interesting terms. Let's look at them. Okay, the first one is the probability of the data given that theta takes on the value x. But if you look at this closely, we observe that this is exactly the likelihood from maximum likelihood estimation, okay? So what this means is we're reweighting the likelihood from previously, okay? And what are the other terms? The other term is the so-called prior, okay? The prior is what captures our prior beliefs that we were talking about. So in a lot of cases, we have reason to believe that some values for theta are more likely than others. For example, as I told you in the coin example, we would expect probably that the value is somewhere around 0.5, even if it's biased, and that an extreme value such as 0 or 1 is less likely. Okay, and this was what is captured by the prior, and this will prevent extreme results and overfitting. Okay. The denominator is not so important. This is just a normalizing constant. It's called evidence and it's useful in for other purposes, but for us it's not so important, so we're not going to take a closer look at it. Okay. What you need to take home from this slide are the three terms: the prior, which is this one, the likelihood, and the posterior, and how they are connected. They are connected by Bayes' rule. Okay. And the prior is our belief in what theta looks like before we observe data. And after we observe data, the posterior is our updated belief in what theta looks like. Okay? And this will turn out to be useful to prevent the overfitting. So we have established a connection between the likelihood that we've been using previously and the posterior distribution, which is of interest for us now. And the link between these two is the prior distribution. And the prior distribution is part of our model. So we get to choose the prior. And the point of the prior is that we have to choose it without looking at observations. And this leaves room for model assumptions because there are no prerequisites that the prior needs to fulfill, except that it needs to be a valid probability distribution, which means that it integrates to 1. And this leaves room for model choices, and these model choices can be and often are subjective. Now that doesn't sound too good in the first place, but it's actually not a problem. We just have to be aware of that. So an example might be that we choose a prior that says that other possibilities than 0, which is the maximum likelihood estimate for this two heads sequence, are possible. That's a very weak prior. A stronger assumption would be this example that I was already talking about, which is that we would assume that the parameter theta is most probably in a region between, say, 0.4 and 0.6, so not too far off from a fair coin, which has a parameter of 0.5. Okay? These subjective assumptions are also sometimes called inductive bias. Okay? So by introducing these subjective assumptions, you're biasing your analysis or your model towards certain solutions. Okay? This is called inductive bias, and it's something that you should be aware of when you're writing down a model.